So we are now going to talk about an example of a machine architecture and see how we could potentially generate code for that particular machine architecture. So we are going to look at a very simple machine, and we also call it a stack machine. And in this particular machine, the only storage is a stack. Now this is different from the typical machine that we are familiar with, which has registers and memory and things. In this particular machine, let's assume that there's only one way of doing storage, and that's a stack. And the instructions are of the form result equals some operation f applied to some number of arguments a1 dot dot an. For example, the operation could be plus, and the arguments could be any integers, 4-byte integers, and the result is also supposed to be a 4-byte integer. Now, what such an operation is going to do for a stack machine, so this is the instruction set of this particular machine. It's going to pop the top n words of the stack, apply f on these popped words, and then push the result on the stack, right? So we're just assuming that there is such a machine that has stack as the only storage. We're also assuming that it has an instruction set, and the any instruction in this instruction set has this particular form and has this particular semantics or meaning. So here are some example instructions. For example, an instruction like push I. So let's say this is a stack, and by convention we're going to assume that the stack grows downwards. So when you have an instruction like push I, it's just going to push the argument I, which is supposed to be a constant here, and it's just going to push that constant to the top of the stack. Now, similarly, there could be an opcode called add, and so add takes two operands. So if there were two operands at the top of the stack, let's say x and y, then it's going to pop off the top two operands. So it's going to remove x and y from the stack, and then instead push x plus y. So it's going to compute the addition and then push the result on the stack, right? So this is the operation of this machine. All right. Here is an example computation. So let's say I wanted to compute 3 plus 4 on this particular stack machine. Then I'm going to first push 3. By dollar I mean it's a constant 3. So I'm going to push the immediate value, constant value 3. Then I'm going to push the constant value 4. And then I'm going to execute the add opcode. The add opcode is going to pop off the top two words, which in this case are going to be 3 and 4. And it's going to push the sum of these two quantities, which in this case would be 7. And we're assuming here that the programmer should expect the result of this program at the top of the stack, and that makes sense because the only storage is a stack. So at the end of a program, we expect the result to be at the top of the stack. Now, before we go further, let's just compare such a stack machine to a typical register machine. A register machine has explicit operands. For example, if I want to say add, I just don't say add, I say add what? So I say add R1, R2, R3. Maybe this means that you're supposed to add R2 and R3 and put the sum in R1. I could use different registers name. For example, I could say R1, R5, R7, and then that's going to do, name different registers. On the other hand, on a stack machine, we just have this opcode called add, and the operands are implicit, because the operands are just the top two words of the stack, and so we don't have to explicitly name them. Now, there are both advantages and disadvantages of a stack machine over a register machine. One of the big advantages is that the instruction opcodes are much smaller, or the instructions themselves take smaller amount of space. As you can see, we just need to have the opcode, and because the operands are implicit, we don't really need to, the instruction size itself is going to be typically smaller. Well, you could argue, although the instruction size is smaller, you may need more number of instructions to perform the same number of operations. But overall, it's for typical type of programs, it is usually considered that it is possible to implement them using shorter code size on stack machines than on register machines. In fact, this was one of the reasons why the Java virtual machine bytecode. So the Java virtual machine is also a machine abstraction, and that was designed as a stack machine because originally Java was supposed to be a language that allows code mobility, and so code was supposed to be shipped over the network, and network bandwidths were low, and so a lot of stress was given on the size of the code. And so one of the reasons that they chose a stack machine for the Java virtual machine was because of this reason. The disadvantage of using a stack machine is sometimes the number of instructions that you require to do the same amount of computation can be more, and which means the program can be slower, for example. But then, it also depends on what kind of program it is, what's the application that we are interested in developing, and it's not necessary that one is going to be faster or slower, or one is going to be bigger or shorter than the other. It is the answer is more nuanced and depends on the application. Now there's a generalization of a stack machine. It's called an n-register stack machine. Conceptually, the idea is let's keep the top n stack locations in registers. And the thought behind using an n-register, generalizing a stack machine to an n-register stack machine, is that there are some values that are accessed very frequently, and so we want to avoid memory accesses, and so let's keep some values in registers. And maybe we want to keep the top n values in stack locations and registers, because that's going to make our code generation strategy simpler, as we're going to see with some examples. And a special case of an n-register stack machine is a one-register stack machine, where there's only one register and a stack, and this unique register is also called an accumulator in such a machine. Okay, so what is the advantage of a one-register stack machine? We can understand this using this example. So in a pure stack machine, if I wanted to do an addition, then I would use the add opcode, and it's going to do three operations. It's going to pop the top word, then pop the second top word, so it's going to do two pops. So it's going to say T1 equals pop, and T2 is also assigned pop, and then it's going to push T1 plus T2, right? So this has three memory accesses, two because of the pops and one because of the push. On the other hand, in a one register stack machine, the add would have different semantics. Notice that we are assuming that the top one location of the stack is already in the register, or which we are also calling the accumulator, and I'm using the ACC abbreviation to represent the accumulator. And the semantics of the add opcode are: accumulator is assigned accumulator plus stack top. All right, so it has a very different semantics. First of all, it is adding value, it is storing the result in the accumulator itself. It's not actually storing the result on the top of the stack. Secondly, it's reading one of the operands from the accumulator itself, so it doesn't need to make a memory access for that. And third, it's actually not changing the size of the stack, right? So it's just that this particular machine has different semantics for its opcode, and in this particular case, I'm assuming that this is the semantics of the add opcode. The accumulator is assigned accumulator plus stack top. Notice that it has only one memory access, and you can see that because of adding one register, I have saved two memory accesses for this simple operation. And so one can imagine that adding registers is going to improve performance, typically because memory accesses are more expensive than register accesses, typically speaking. All right. So how would you operate a one register stack machine? So let's say you wanted to compute an expression OP applied to n arguments E1 dot En. For example, OP, the operation could be plus, and then E1 dot En could be integer constants. Now here is one strategy, right? So this is just one of the potential strategies, but it's one of the it's simplest and probably the easiest to understand, and also the natural strategy for this kind of an architecture. For each EI, so E1 dot En, so for I from 1 to n, for each EI, compute it in the accumulator. So first we compute, let's say, E1, and we compute it in the accumulator. Then we compute E2, compute it in the accumulator. But then by the time we compute E2, we want to also preserve the value that was computed for E1. And so before we compute E2, we push the value of E1, right? So the other part of the strategy is you push E1 dot En minus 1 to stack as they are computed. Okay, so I computed E1 in the accumulator, but then before I start computing E2, I push E1 to the stack. Pushing into the stack basically means I've sort of saved that value because I may need it later to actually compute my operation, right? After I've computed all the operands. And then E1, E2 is going, E2 is going to do overwrite, clobber my accumulator, but hopefully it's not going to overwrite the top of the stack. If it needs some storage space on the stack, maybe it's going to push on the stack, but never override the value that I saved for E1. And then I eventually evaluate the operation and store the result in the register, the accumulator. And finally, when I am done, I want to pop off the top n-1 words from the stack so that the stack looks exactly as it was before this computation started. Okay, so here's an example. Let's say I wanted to compute 7 plus 5. Then I would say push 7, that's going to push the constant 7. Put 5 into the accumulator, add, and that's going to execute this particular operation. Accumulator will get 7 plus 5, and one thing that's missing is that I may want to pop. Alright, so basically clear the extra space that I had used on the stack for saving 7. Alright, so here's the invariant that I want to follow. After evaluating an expression E, the accumulator holds the value of E, right? So that's the invariant that I'm using in my code generation strategy. For example, when I compute E1, I assume that after E1 has been computed, the computed value is stored in the accumulator. So the accumulator holds the value of E, and the other invariant that I'm following is that the stack is unchanged. So the stack is unchanged. So if I start computing E, whatever was the value before the starting of computation of E is also the same contents of the stack at the end of computation of E. And that's something that I'm going to maintain as my invariant during this code generation strategy. So in other words, expression evaluation will preserve the stack in our strategy. So for example, if I wanted to compute 3 plus 7 plus 5, then I would first compute 3 and put it in the accumulator. Then I would save this value from the accumulator to the stack. And then I would go on and try to compute 7 plus 5. Now notice that 7 plus 5 is going to also maybe push and pop from the stack and is going to clobber the accumulator. But because I have the invariant, that's the evaluation of 7 plus 5 will not change the stack as it existed before the start of this evaluation. The value 3 would still remain intact in the stack. So here are the steps that would be involved in kind of generating the code. Or this is what the generated code would look like. It would first evaluate 3 in the accumulator, save this value 3 to the stack, evaluate 7 in the accumulator, save the value 7 to the stack by pushing, not overwriting, evaluate 5, and then now we are kind of ending our, now we are ready to do the first addition, which is the 7 plus 5. So I'm going to say add. That's going to put 12 in the accumulator, and then I'm going to do pop stack. That's going to remove 7 from the stack. And then finally, I'm going to compute 3 plus whatever was the result of 7 plus 5. So I'm going to say the result of 7 plus 5 is already in the accumulator. 3 is on the stack, so I'm going to execute add, and that's going to put 3 plus 12, 7 plus 5 into the accumulator. And then I want to pop the stack to basically get rid of the saved 3 value, which I no longer need. Okay. Notice that steps 3 to 6 are basically computing 7 plus 5, and steps 1, 2, and 7 are basically computing the top level expression, top level operation of addition. So this just represents a code generation strategy, and there could be different code generation strategies. Here in this strategy, the evaluation is being done left to right, and that's just a matter of choice. For example, we decided that we were going to first compute 3, then look at the next expression, which is 7 plus 5. We could have done the other way around. We could have first computed 7 plus 5 and then computed 3. The reason we could have done the other way around is because addition is a commutative operator. Some operators are commutative, others are not. Depending on what the operator is, we could choose what strategy we want. If the operator is not commutative, then the order is specified by the operator. If the operator is commutative, then the order is specified by the code generation strategy. In this case, our strategy decides to do the evaluation left to right. Okay, what about optimization? Is this an optimized code or is it just some code? right? So actually this machine is rather narrow in its interface. It only has stack as a storage, and there's a very limited instruction set that we can do. And maybe there are opportunities to optimize here, but the way we generated this code, we really didn't worry too much about optimization. Perhaps the only things that we cared about while in terms of optimization was where to store the result. So we basically, the choice of storing the result in the accumulator was sort of based on this assumption that accessing reading and writing to the accumulator is going to be cheaper than reading and writing to memory, and so it makes more sense to keep the most recent values in the accumulator, because they are also going to be the most likely used values that are going to be used in the near future. Other than that, we haven't really done much optimization here. Also, the scope for optimization is not that much. The whole premise of optimization is that there should be a lot of redundancy. There should be many different ways of doing the same thing. And only then it makes sense to choose the best way of doing that thing, right? So if there are, for example, in a real machine, there will be lots of ways to compute the same function. And so optimization is basically about finding a better way to do the same function. In this particular machine, though, that space of potential solutions is not that large. And so that is also a reason why optimization is not such a big issue. And we haven't even discussed optimization in this context yet. Here's what the generated code would look like. It's just the pseudo code for the steps that I had in English earlier. Accumulator gets 3, push accumulator gets 7, push accumulator gets 5, add plus pop, which is add, execute add, and then execute pop, and then again execute add and execute pop. I'm just putting add plus pop in a single row. Actually, there are different instructions, but just putting it in a single row for easy readability. Here's what the code generation strategy for something like this would look like. I'm assuming that my input programming language, the higher level language, is the language of expressions. That is just computing some operations on some constant integers. For example, examples like we saw 3 plus 5 or 3 plus 7 plus 5 and things like that. And so the code generation strategy that I've just described informally would look something like the following. There would be a function called cgen that's going to take as input an expression and output the set of instructions that are going to implement or compute that expression. So for example, if the expression is just a single constant, const, for example 3, then codegen for 3 is just going to have the instruction which just assigns that constant to the accumulator. All right, because in a code generation strategy, the only the invariance that we are following is that the result is in the accumulator, and we are not clobbering the stack in any way. And this particular rule of code generation is following both those invariants. Now let's look at another rule. Just using examples, we're going to see this in more detail. Codegen for a plus b, where a is an expression and b is an expression, involves first codegening a. Then after codegen for a is complete, then I can assume that the result of A is an accumulator. Then I do push accumulator, so push it on the stack, save it on the stack. Now I can do codegen B, and I can be sure that codegen B is not going to clobber my pushed value. It can clobber the accumulator, but it will not clobber the pushed value because of my invariant. And then after I've done codegen of B, I'm going to execute the add instruction, because at this point I know that the accumulator contains the value computed for B, and the top of the stack contains the value computed for A, and so I can execute add to get the addition result in the accumulator. And finally, I want to clean up the stack by using the pop instruction.